Hi and welcome to video 3 for section 1.5. This is a pretty short video, but short doesn't mean not important. In fact, this video is going to be about one of the most important things you may learn all semester, and that's why I gave it its own little segment. And it's what's known as the intermediate value theorem. Usually you see it, tell you guys all the time, math people are lazy, so we say IVT, Intermediate Value Theorem. So here's the official definition. Then I'll kind of explain in layman's terms what we're talking about here. Suppose f is continuous on the interval, closed interval, AB, and let n, capital N, be any number between f of A and f of B, where f of A is not equal to f of B. So we're not picking the same value here for f of A and f of B. Then there exists a number C in the interval A to B such that f of that value C is equal to this number n that we picked. So graphically, what this looks like, so let's say I have some point here, this is my value A, and I have some curve, goes to this point here, which is B. So if this is my value A, if I come back to the y-axis, this is what? This is f of A. And similarly, if that wasn't very straight, if I come back to the y-axis from the top point, that's my f of B. So now, if I pick some number n between f of A and f of B, so let's just call it some point there, n. This is a continuous function, so there's no discontinuity. I don't have to jump or lift my pencil. So if I come across here, hit the graph and come down, that gives me some point here, C, that is between my values A and B, that if I do f of C gives me this value n. Where this is commonly used, and where you're going to see it a lot here, is in determining if there's a root within some specified interval. So let's look at a little different graph here. So a root means what? A root means that f of that, if you plug that value into the function, it gives you what? It gives you 0. So if I have some function, let's say my function is here, and this is my A, and this is my B. If f of A, and it could be flip-flopped, A could be above the x-axis, B could be below. So my A is actually here, sorry. So if my A comes down and comes over, my f of A is what? Well, this is some negative number. Who cares? It's just negative for our purposes here. If B is here, if I come across, f of b is what? Well, that's a positive number. So if I start below the x-axis and end up on a continuous function above the x-axis in some specified interval, it means what? It means there has to be some point along this function where I cross the x-axis, so let's call this c, where f of c is what? 0. So the only way that I can get from below the axis to above it is by crossing the x-axis, and the function evaluated at that point is 0. And so that's where the intermediate theorem is so powerful. If we can pick our endpoints, plug them into the function, one is a positive number, one is a negative number, then it means that within that interval that we just specified, there has to be a root to that function. So let's look at an example. So let's say we want to show there is a root of the polynomial 4x to the third minus 6x squared plus 3x minus 2 is equal to 0 between, or within the interval, 1 and 2. I'm not trying to find the value that's a root. I just want to show that there is a root. So somewhere on the graph here, between 1 and 2, if I plugged in that number into the function, would it tell me that this function is equal to 0? So I'm going to do what? By using the intermediate value theorem, first I figure out f of 1, then I figure out f of 2. If they're different signs, one positive, one's negative, I know there has to be a root. What if they're both positive? Or what if they're both negative? Then I can't really say, right? Because let's say this is 1 and this is 2, and my value for 1 is positive and my value for 2 is also positive. Does that mean there's a root in here? I don't know. It's inconclusive. Why? Because this thing could just maybe do something like that, or maybe it comes down and just touches the axis, it never crosses, or maybe it actually does cross and then comes back up. So they're both positive, but I have what? I have 2 roots in here. But I can't use the intermediate value theorem to show that. So the intermediate value, I'd have to keep picking smaller intervals to see if in fact it actually worked. But if I'm giving these 2 points and it says show there's a root, it's the quote I tell you guys all the time. The essence of math is to make complicated things simple, not simple things complicated. So all you're doing is plugging in 1, plugging in 2 into the function. So f of 1 is what? It's 4 times 1 to the third minus 6 times 1 squared plus 3 times 1 minus 2. So this is 4 minus 6 plus 3 minus 2. So that's what? 4 minus 6, negative 2, plus 3, positive 1, minus 2, negative 1. How about f of 2? Same thing, just plug it in. So 4 times 2 to the third minus 6 times 2 squared plus 3 times 2 minus 2. 2 to the third is 8. 8 times 4 is 32. 2 squared is 4 times negative 6 is minus 24. 3 times 2 is 6, minus 2. So 32 minus 24, positive 8. Plus 6 is 14, minus 2 is 12. So if I was to draw this on a graph, these 2 points, so f of 1 is equal to negative 1. So that's here. f of 2 is positive 12. So up here. So I don't know what happens in between here, but at some point it has to cross the x-axis to get from 1 to 2, which means there has to be a root there. So by the intermediate value theorem, there is a number c such that f of c is equal to 0, i.e. there is a root between 1 and 2. So that's it. Like I said, short of quick video, intermediate value theorem, how do we use it? This is how we use it. So come on back, we'll look at section 1.6 and that'll wrap up chapter 1.